Hello everyone, welcome to chapter 2, measurements in chemistry. First part of chapter 2 is dealing with measurements. Measurements are made on a routine basis. For example, measurements are involved in following recipes for brownies, determination of our heights and weights, and in fueling our cars with gasoline. So a measurement is the determination of the dimensions, capacity, quantity, or extent of something. And we have two different systems of measurements. The English system, which is used for commerce, which uses things like feet, pounds, inches, quarts, gallons, inches. And then we have the metric system, which most of the rest of the world seems to use. Common units there are grams, meters, and liters. Jimmy Carter tried to convert us to the metric system, but stubborn Americans revolted and we stuck with the English system. Second part of chapter 2 deals with metric system units, where there's only one basic unit for each type of measurement, one unit for length, mass, and volume, etc. By looking at those basic units, we can add prefixes to change the size of that particular unit. The prefix is independent of the base unit and can be used on many other base units as well. Here are some of the common prefixes and symbols that the metric system is going to use. Giga is noticed with a capital G, mega with a capital M, everything else seems to be lowercase. There's kilo with a K. Notice we're getting into small parts here. Deci is going to be 1/10 of a unit, so if you like fractions, 1/10. Centi is 1/100th. Notice the lowercase c. Milli are the tiny little marks on our meter sticks that we'll see when we're in the lab. Symbol is lowercase m. It's 1/1000. Come to our first Greek letter. It's known as a mu, or it's a U with a long tail on the front, and it means 1/1,000,000th of whatever unit we happen to be talking about. Nano, we're getting into the wavelengths of lasers and light. Okay, that's a lowercase n, and it's 1/1000,000th. Pico is 1/1,000,000,000th. And the way that I put most of these in order is I have this acronym: King Henry dances merrily during cold months. Where this is kilo, this is hecto, which isn't on your chart, but it would be right here, and it stands for 100. Then deca, which would be right in here, it's DA. And then we actually have our base units, which I usually put as meters, so this is our base. But it could be meters, grams, liters, moles, whatever have you. That's our base unit. And then we have deci, centi, and milli. So King Henry dances merrily during cold months. That puts most of our prefixes in order and allows us to move our decimal pretty easy. And it also goes down by a 0 every time. So this is 1,000 here, 110. This is our 1 spot right here. Then 1/10th, 100th, and 1,000th. And we'll see how to use that shortly and repeatedly throughout the semester. This brings us to one of our first learning checks for this chapter. We're going to try to fill in the prefix or mathematical value dealing with that prefix. So I always encourage you to pause the video and try to stop and see if you can get the answers. Otherwise, let's get right to it. So giga, that's capital G. You can put that right here. Giga, and that is 1 billion. So you could just write 9, 10 to the 9th. In your calculators, you might see that as e to the 9th, just in case you ever see that. That really just tells you that there's 9 zeros that it's taken spot of. Nano, symbol is a lowercase n, that's 10 to the minus 9. In this case, it gives you 10 to the 6. That is mega, and it looks like this. And this is our Greek letter mu, and that is micro, and it's 10 to the minus 6. Metric unit for length happens to be the meter, which is symbolized by a lowercase m. It's pretty close to a yard. 1 meter is equal to 1.09 yards, so just to give you some idea. And that is the metric system, the base unit for length. Length is measured by determining the distance between 2 points. And on our previous slide, we said that King Henry dances merrily during cold months. Whoops. So this right here, that is our base unit for length. Remember, this could be grams, liters. This was an M here. The metric unit for mass is going to be the gram, symbolized by lowercase g. Mass is measured by determining the amount of matter in an object. And weight is different than mass. Mass is universal no matter where you go, whether you're here, you're on the moon, or you're floating out in outer space. Weight is dependent on the force of gravity. So you would weigh 1/6 on the moon that you do here on Earth because the gravitational force is 1/6 of that here on Earth. The base unit for volume happens to be the liter. Volume is a measure by determining the amount of space occupied by a three-dimensional object. And a conversion here, 1 liter is equal to 1,000 centimeters cubed, or 1 deciliter. 1 milliliter is equal to 1 centimeter cubed. Milliliters are usually used for gases and liquids, while 1 centimeter cubed is generally used for solids. Here's just a picture showing you that a 10 centimeter by 10 centimeter by 10 centimeter cubed is equal to 1 liter. And notice that they use capital L for liters, because if you use the lowercase l, it's a lot of times confused with the number 1. Here is another learning check. Again, I encourage you to pause the video, try to fill in the blanks and see how you do. We're going to start to fill in the blanks. So kilograms, grams is a measure of mass, and that happens to be kilogram. Megameters, meters is a unit for length. And writing our symbol, notice the capital M and the lowercase m. Nanogram, grams are used for mass. And milliliter, notice the capital L. Oh, that actually goes over here. And this should have been length. Another learning check for us. Again, I encourage you to pause the video and then try to arrange these from smallest to largest. Doing it for number 1 would be microliter. That's that mu. I'll make it a little bit better. Microliter to milliliter to gigaliter. For B would be centigram to decigram to megagram. Next, we would have picometer to micrometer to kilometer, and then finally nanoliter to milliliter, and then to centiliter. In scientific work, numbers are grouped into 2 categories: exact numbers and inexact numbers. Exact numbers is a number whose value has no uncertainty associated with it. That is, it's known exactly. So when you get a dozen eggs, you know that there are 12 of them. There are many examples like that. Counting marbles. Simple fractions are another example of exact numbers. Inexact numbers is a number whose value has a degree of uncertainty associated with it. Inexact numbers may result anytime a measurement is made. It's impossible to make an exact measurement. Some uncertainty will always be present. Flaws in measuring device constructions, improper calibration of instruments, and the skills or lack thereof possessed by the person measuring with that device can all contribute to error or uncertainty. Uncertainty in measurements. We are going to include all the digits that we're absolutely sure of. So if we were to take a look at a graduated cylinder in laboratory, give me a second to draw this here real quick. Let's say this is 5 milliliters right here. This is 10 milliliters up here. Each one of those represents 1 milliliter in between. So this is 6, 7, 8, and 9 here. And we were to fill our graduated cylinder with water. First thing we would want to do is set it level on a surface, get down eye level with it, and read the bottom of the curve. So we know that it's at least 6 milliliters. We want to estimate 1 digit beyond the numbers that we're certain of. So somebody in your group might say that it's 6.5. This first digit we're absolutely sure of, and this is our estimated digit right here. Somebody else in your group might say, no, I think it's 6.4. Either one of those would be acceptable answers because you're estimating this last digit right here. Here's another learning check. So again, I encourage you to pause the video and see if you can get whether these numbers are going to be exact or inexact. The fact that we have 32 chairs, that's an exact number. There are 60 seconds in a minute, no question that's exact. A bowl of cherries weighs 3.2 pounds. That's not an exact number. That's a measurement, and we are always some uncertainty in there. A newspaper article contains 323 words. That's exact. Here are some better pictures in the graduated cylinder that I drew. Okay, notice that we're starting right at the 0 mark and not at the edge of the ruler. There are a couple different scales here. The first block reads 3.7. We know that it's at least 3, and we're estimating that it's 0.7 centimeters. Not a full centimeters. The next one we can be a little bit more precise because there's more marks on this ruler, so those marks on there, the numbers are centimeters, the little lines in between are millimeters. So we know that it's reached the 3.7 mark right here, but it's a little bit past that, so the estimated digit here is 3.74. We know that it's 3 and the 7 are certain, but our estimated digit is the 4 at the end there. So measurements made with ruler A will have a greater uncertainty than those made with ruler B. Ruler B is therefore more precise than ruler A. Here's another learning check for us. We're measuring paper clips using different scales. And using ruler number 2, hopefully, just like in the previous slide, you should know that there are going to be 3 digits. Okay, 2.7 something. In this case, the answer is 3.70. The user thought it was perfectly aligned with the 7th mark. The next one, you got to pay attention to the scale because it goes up by 10. So the user may have thought that this one was around 27 centimeters. The 2 we know for, the 20 we know for exact, the 7 is our estimated digit. The fourth part of chapter 2 is dealing with significant figures. And this will be something that shows up throughout the semester, and that's looking at when we have measured digits, how do we record the number of significant digits? And significant figures are all the known digits plus that estimated digit. So there's a little formula, and we'll look at some rules on how you determine the number of significant figures in a measured number. Some of the guidelines for determining significant figures are on the slides to follow, but all non-zero digits in a measured number are said to be significant. So that's the numbers 1 through 9. So in this case, 3,456 has 4 significant digits. All these non-zero digits always count as being significant digits. Somebody took the time to measure those. Our next rules are for zeros. Zeros tend to be the tricky parts for individuals. So leading zeros are never going to count. These are leading zeros that occur before a number, so something like 0.008. There's really only one significant figure in that number. Here's another example. 0.048 has 2 significant figures. So what I like to do is I like to draw a line right through those leading zeros because they never count. Confined zero, or sandwich zeros as I like to call them, those are situated between non-zero numbers. These ones always count as being significant. So notice this 0 right here is sandwiched between the 6 and the 7. Those sandwich zeros will always count. So there's 4 significant figures there. And the last one is for trailing zeros. To the right of a number, and notice they are significant only if the number contains a decimal. So we got to watch the decimal. We'll look at a few examples. This one, there is a decimal there, so it's 9.300. There's 4 significant figures. If it were just 9,300 with no decimal present, that's when they don't count. Okay, and this one would only have 2 significant figures. I like to call them sig figs. So if there is a decimal present, then these trailing zeros count. If there's no decimal present, those zeros do not count. Here's some learning practice for us. So again, significant figures are tricky for people, so it takes some practice. So I encourage you again to stop the video, try them, and see if you can get the answer. So in A, leading zeros never count. All those 4s do. There's 3 significant figures there. Again, leading zeros don't count. All those 4s count after the leading zeros, so there's 3. Leading zeros don't count, but that one's sandwiched, and this one is trailing after the decimal, so there is 4 significant figures there. And then all these leading zeros never count. Only 1 significant figure there. Determine the number of significant figures in this one as well. So leading zeros don't count. 3 significant figures because the 3, 7, and 2 always count. Leading zeros don't count. 3 significant figures. Leading zero doesn't count, but that one that's sandwiched does. There's 5 there, and we have a leading zero, and then a couple trailing, but after this non-zero digit. So these zeros do count here, so there's 5 significant figures there. Just some more practice. Again, try to get these without my help. So in this case, these 3 digits out in front do count, and the ones that are trailing after the decimal always count. So there's 5 significant figures there. No decimal present, so these ones don't count. Only 3 significant figures. No decimal point at the end. These trailing zeros don't count, so there's 3 significant figures there. 2 at the end don't count because there's no decimal, but the one that's sandwiched there does, so that looks like there's going to be 5 significant figures there. A couple more to practice. These ones are significant because there is that decimal there, so there's 5 present there. Letter B, this one counts. It's sandwiched between the 3's, but these ones don't count, so there's only 3 significant figures there. These ones don't count, no decimal present. This one does. It's sandwiched, 4 significant figures there, and then we have 3 sandwiched zeros there, so there's 6 significant figures. A little bit more practice with significant figures. Which following pairs of numbers do both members of the pair contain the same number of significant figures? Well, let's just go through each one and see, but I encourage you again always to pause. So this one has 4 significant figures. This one also has 4, so that one is the same. This one, the sandwich zeros count, so there's 4. This one at the end where there's no decimal present, that one only has 3, so not the same. Leading zeros never count, so there's only 2 in this one. This one doesn't have a decimal. These trailing zeros don't count, so there's 2 and 2, so it's the same. Leading zeros don't count. These ones trailing after the decimal do, so there's 4 in this one. Leading zeros don't count. This one's sandwiched, and this one's trailing afterwards, so that one also has 4. It's the same. In which of the following pairs of numbers do both members contain the same number of significant figures? So it's very similar to the previous question. So we'll just go through them all. Leading 3 there. There's 4 here, so not the same. This one has 4. This one only has 3, so not the same. Leading 0. Trailing zeros after the decimal. This one has 4. This one only has 2, so not the same. And this one has 3, and so does this one because there's no decimal to present. So 3 and 3, same. Just some real quick rules for rounding. The process of deleting unwanted or non-significant digits from a calculated answer. If the first digit to be deleted is 4 or less, simply drop it and all the digits following. So if you're going to round this to 3 significant figures, you look to the 4th one, see it's 2, and you drop 2, 9, and 8 because it's not big enough to make us round the 3 up to a 4. For rounding up, if the first digit to be deleted is 5 or greater, that digit and all the following are dropped, and the last retained digit is going to be increased by 1. So if we were looking at this for 3 significant figures, notice the 4th one is a 5. It's big enough to make us round the 6 up to a 7, and thus giving us our answer of 7.87. A little bit of practice rounding with the certain number of significant figures. So we want 4 significant figures, so remember that leading 0 doesn't count. Look to the 5th digit. It's big enough to make us want to round up. So our answer would be 0.3508. 3 significant figures, we look to the 4th significant figure. Not big enough to make us round, so we leave it as 13.4. 2 significant figures, that would be the second one. We look to the 3rd digit. It's not big enough to make us round up, so this one would just be left as 22. 3 significant figures, remember these leading zeros don't count, so here's our 1st, 2nd, 3rd, and 4th significant figures. We look to the 4th one, not big enough to make us round up, so 0.0303. Looks like the next one is a very similar question. We want 4 significant figures, so we look to the 5th digit and we look to that 7. It's big enough to make us want to round up, so 340.3. 3 significant figures, we look to the 4th significant figure. It's not big enough, so 133. 2 significant figures, remember those leading zeros don't count, so 4, it's our first, second, and third significant figure. The 7 is big enough to make us want to round up. And our last one, 3 significant figures, we look to the 2, the 4th significant figure there, not big enough to make us round up, so 0.357. Now that we have learned about significant figures, we're always going to have to do something mathematically with them. So when we're multiplying or divide, we really pay attention to which one is the least precise measurement, and we match our answer to it. So in our example here, when we're looking at our numbers, we have 4 significant figures here, we have 5 significant figures here. In our calculator, it might spit something like this out, but we can only technically have 2 significant figures in it, and that's why we round it up. So that the 3rd significant figure was big enough to make us round it up to 7.4. The second type of mathematical operation that we might have to do in our class is add or subtract. And this time we pay attention to the numbers after the decimal. So you can see in our first digit, we have 3 digits past our decimal, and our second number we have only 2 digits past our decimal. So in our calculated answer, we really only want 2 spots past our decimal. So we look at that 5, it's big enough to make us round the 7 up to an 8, and that's how I get my answer. So you got to pay attention to what type of mathematical operation you're doing in order to get the right number of significant figures. Again, I encourage you to get your calculator out, try these mathematical operations, and see if you can answer based on the correct number of significant figures. So when we're looking at the first one, all these zeros are going to count. So there's 5 significant figures there. All the zeros count in the next one. There's 3 significant figures there, and there's only 2 significant figures in this one. So when we're multiplying, we can only have 2 significant figures in our answer. So when you do it in your calculator, you have to leave it like this. These leading zeros don't count, but this trailing one does, so that's why there's 2 significant figures there. In B, there's 5 significant figures in this one, only 3 here, so you should only technically have 3 significant figures in your answer, and when you do it in your calculator, you'll get something like this right here. All the other ones after that 3 should have been eliminated. Following the same logic, again, we're multiplying. So there's 2 significant figures in this one, 2 significant figures in this one, and 4 over here, so I can only have 2 significant figures in my answer, and when I do that in my calculator, my answer is going to be 14. I rounded appropriately, and I only have 2 significant figures in my answer. When using exact numbers in mathematical operations, they're said to be exact. There is no uncertainty with them, and they possess an unlimited number of significant figures. So 1 inch is equal to 2.54, exactly, and there's no uncertainty there with that conversion factor. 9 pencils, no uncertainty, so you got to use the other numbers that's associated with it to figure out your significant figures. In chemistry, we use a lot of very big numbers, and we use a lot of very small numbers. So rather than keeping track of all those zeros, a lot of times we'll put numbers in scientific notation. And that is just a number expressed in this form right here, where A is a number between 1.0 and 9.9, and then it's multiplied by a factor of 10. So A is going to be that coefficient between 1 and 9.9999. N is a whole number that represents really our decimal places. Here's an example of what it might look like. 1.07 times 10 to the 4th. Sometimes you might see this written in your calculator as 1.07 e to the 4th. This e really says that my exponent is to the fourth, and e takes the place of this right here. And you get to it in your calculator by hitting second function. Usually it's a comma on most graphing calculators, and it says EE in the background. That's how you get to that exponent in case you need to use it in your calculator. Converting from decimal to scientific notation, the decimal point in a decimal number is moved to the position behind or to the right of the first non-zero digit, and the exponent for the exponential term is equal to the number of places that it has moved. So when we take a look at this one, we want our decimal point over here behind our first non-zero number. Those are all significant figures, so we're going to include those. Notice I moved my decimal 2 times. That's how I get my exponent of 2. My number is big, so my exponent is big. And the next one, we have a very small number, so we're going to take this decimal and move it over 1, 2, 3 times. That's how I ended up with a -3. Very small number here, very small exponent. But these leading zeros don't count. Okay, so don't include those, but this one trailing after the decimal does count, so I have to include that one in my answer. Just going to practice these just a little bit. Converting numbers into the scientific notation with the correct number of significant figures. So move this decimal over 1 time. This is going to be 3.722 times 10 to the 1. This time I'm moving it the other way, so it's going to be 1.02 times 10 to the -3. This one just moved over 1 time. It's going to be 3.4000. I included all those zeros because they're significant, times 10 to the 1. This one, move that decimal. That's a comma right there, so I got to move it over a total of 5 times, and I end up with 2.34 times 10 to the 5th. This, we're going the other way. We're going from scientific to a decimal form. So when my exponent's big, just move that over 3 times, or 2 times there, sorry. Move this one over 2 times again. So it's 234.00. This time I move my decimal. I have a negative exponent. Move it over 1, 2, 3 times. 0.00234. And same thing here. 1, 2, 3. And you can put those zeros in the front if you want. Next part of this chapter deals with scientific notation and really multiplying and dividing with scientific notation. Most of the time the calculator does this for us, but in case you want to do it longhand, if you're multiplying exponential terms, you actually add the exponents. And when you divide the exponential terms, you subtract the exponents. Seventh part of this chapter deals with conversion factors. And that's just a ratio that specifies how one unit is related to another. Most of the time I'll give you any conversion factors that you might need, but it allows you to convert from one unit to another. So here's an example. 1 foot is equal to 12 inches, and you could set that up as a fraction in 2 different ways. So they're not making these up, they're just going to take this and convert it into 2 different fractions. You might need it in one situation or another, but setting these up and paying attention to the units on the end is so very important and will show up throughout the semester a lot. So get in the habit of labeling everything properly with units. Here is just some common comparison from one unit to another conversion factors, and then notice they set them up in both ways. Eighth section of this chapter deals with dimensional analysis, and these are steps for using and setting up dimensional analysis. But basically, all about watching those units. So identify the given quantity and the unit that go along with it, and I like to put it as the start of a fraction. Next, you're going to multiply it by the conversion factor that you're trying to use and set it up in such a way that your unwanted units get canceled out by being on opposite sides of the fraction, leaving only your desired units. And then you do the mathematical operations so that you can finish the problem. So here's an easy example of using dimensional analysis in order to solve a problem. So a golfer putted a golf ball 6.8 feet across the green. How many inches does it represent? So we need to know that 1 foot is equal to 12 inches. And what I like to do is I like to put my 6.8 feet, that's over 1, and then I'm going to multiply it by my conversion factor. So I set up this bridge or this fraction right next to it. But notice that feet are up on top. I want to take my feet and take the number with it and put it on the opposite side. So 1 foot will go here. 12 inches will have to go on top. And notice that the feet will drop off. Anything that's diagonal will cancel like that. The only thing that's left for my unit is inches. In my calculator, I'll multiply the numbers straight across the top. I'll get an answer. I'll multiply the numbers straight across the bottom. I'll get an answer on top and bottom of my fraction, and then I reduce. In this case, it's going to be 1 on the bottom, so I don't have much to worry about there. So the next few slides will take us through that. There's the 2 ways that I could set it up, but I know that I'm going to use the one that I had in the last example to cancel out those units. That's the way that your book will set it up. Notice the feet are on opposite sides. Imagine that there's a fraction right here. And again, the feet opposite sides, they drop off. Multiply the numbers on top. And you get 82 when you're done. Here's another example that I'll set up for you. So an iron sample has a mass of 4.5 kilograms. What's the mass in grams? So 4.50 pounds here. I'm going to set up my conversion. First thing I want to do is take the units, pounds, get it on the opposite side. Take the number that goes right along with it. So it's going to be 2.2046 pounds here. 1 kg is going to be up on top. Okay, my pounds have now been eliminated, but it wanted it in grams, but I'm in kilograms. So I use the second conversion. 1 kilogram, 1,000 grams. Notice I'm labeling with units. I'm watching that they drop off. I'm going to multiply straight across the top, get an answer. Multiply straight across the bottom, get an answer, and then I reduce my fraction when I'm done. So here it is all set up, showing the canceling of units. And there is my answer. Notice 3 significant figures. I started with 3 significant figures. I ended with 3 significant figures. I may have had to put it in scientific notation, but that's okay. I could have answered it in standard form as well. I'm not going to do all of these problems here, but I wanted to show you the shortcut that I alluded to earlier, and that is King Henry dancing merrily during cold months. So in the first one, we want to convert milliliters into liters. So milli is right here. Remember, this could be liters, grams, whatever. All I got to do is take my decimal and move it over 3 times to the left. So my number was 250. Decimal is right here. Move it over 3 times in the same direction, and that's equal to 2.5 liters. Next one, you're going from milliliters to liters, so you're going the opposite way. Oh, same way, actually same exact setup. So 450, my decimal is at the end here, move it over 3 times, and I end up with 0.45 liters. I'll do one more with you. So 100 or 1550 grams, and I want to convert that into pounds. So you look up here. Here's conversion factor for you. I'm going to set this up in such a way that my grams will cancel out. 454 grams all over 1 pound. I'm going to do a little multiplication in my calculator with the numbers on top. And this is 81. And then divide by the numbers on the bottom, and I end up with 3.41 pounds. All right, you should try some of the other ones. I'll give you the answers here. For 82, it's going to be 6.6 times 10 to the minus 6 pounds. 83, it's going to be 0.0066 gallons. And the last one will be 6.42 times 10 to the 4th milliliters. Section 9 is all about density, and it's really just the mass to volume ratio of an object. Units that are common for solids are grams per centimeters cubed, or liquids are grams per milliliter. And our formula looks like this, and I want you to try to remember that density always breaks your heart, right in half. So if we take a look, hopefully you can see that it looks like an M on top for the mass, V on the bottom for volume. And now you can always remember that about density. You can always make these little circle charts that take the algebra out of it. So if you're looking for something, you just cover it up or eliminate it. So if I'm looking for volume, I can cross that off, and I have my mass divided by my density. Makes your life a little bit easier. You can do that with any variable in that equation. Here's just a sample problem where they're trying to figure out the density of the mineral. Mass is given as 17.8. Volume is given as this. Here's our equation. Take our mass, plug it in here. Take our volume, plug it in there. You end up with something like this, and then you just divide two numbers and you get your answer as this right here. Here's another example of a density problem. In this case, we're looking for what is the mass. Whoops. So our mass is unknown. This right here is our volume, 49.6 milliliters, and it tells us that the density is 0.85. So we can use the circle chart, we can use algebra. We're looking for a mass, so we would want to multiply by our volume times our volume to get mass all by itself. Or if we use our circle chart, just cover that up. You have density times volume, just like we have right there. Plug it in our numbers, or you could cross multiply if you're good with algebra, and you end up with 42 grams as your mass. Last part of chapter 2 is all about temperatures, and there are 3 different temperature scales that we'll encounter in here: Celsius, Kelvin, and Fahrenheit. Here is a way to convert between our temperature scales. So Kelvin is equal to our Celsius plus 273, and I like using fractions better than, or I'm sorry, decimals rather than fractions. So Fahrenheit is equal to 1.8 C plus 32. You can use fractions if you want, okay? Or you can use this right here. Whatever works best for you. We just have a little bit of practice here at the end dealing with density. So remember, density is equal to our mass divided by our volume. So our mass is right there. Our volume is right here. All we got to do is divide those two numbers. And for this one, you should end up with 13.55 grams per centimeters cubed. Looks like we're doing the same thing. So they're giving us our mass, they're giving us our volume. All we got to do is plug these numbers into our equation. 12 goes here, the 2.69 goes here, and for 92 you should end up with 4.46 grams per centimeters cubed. And in 93 we're looking for what is our volume. So density is equal to our mass divided by our volume. We're going to cross multiply across the equal sign, so volume is equal to our mass divided by our density. 20 grams goes up on top, density goes on the bottom, and when you do it for 93 you should end up with 25.3 milliliters. Here's a little bit of practice with our temperature scale conversions. Okay, we're looking for this temperature to be converted into Celsius. So remember, our Fahrenheit is equal to 1.8 Celsius plus 32. 95 would go in here. And then it's just a little bit of algebra. Subtract your 32, get an answer, divide by 1.8, and you end up with 35 degrees Celsius. Here's another one where we're at our Celsius and we want our Fahrenheit temperature. So again, here's our equation. Plug in this right in here. So 1.8 times negative 38.9. Sorry about the chicken scratches there, plus 32. And for 105, you should end up with negative 38 degrees Fahrenheit.